Alright, so I'm back with another video, and it is a Codeforces video helping the nature Div 2C recent contest. And I just really like the problem. Like, it was a really nice problem. And lately, I've been doing more Codeforces problems just because I'm liking the problems on there. Even though, sometimes getting TLE on test case like 90 when there's like 100 test cases is really annoying, but um, I feel like I like the Codeforces problems, and I'm probably going to post more Codeforces solutions. And for this one, I like the problem, and I kind of want to explain it more. So we're gonna do this. I'll also explain the code in the same video too, because I already have it here. And essentially, let's get to it. So you can read the problem. It's very easy to read. Just pause the video and read it. I don't need to explain it. It's very self-explanatory, honestly. What you're trying to do is story. You have a bunch of arrays. You can either choose the ith prefix and decrease every element in that prefix by one, or choose the ith suffix and decrease every element in that suffix by one, or you can choose the entire array and increase every moisture um, by one, or increase every element by one. So we have these three operations, and we want to know the minimum number of actions he needs to perform to make the moisture of each tree equal to 0. So first notice that n max n. So let me use this in black. Actually, it's more practical color. Oops. First notice that n is 2 times 10 to the fifth. So we're looking for most likely a linear solution. I mean, sorting this, you can't really sort this. There's no sorting going on in this question, obviously, and this isn't really binary searchable. Like you can't really binary search anything. It's just not a good approach if you're trying to go for a binary search. You'll kind of get to a dead end. Nothing is really like obviously monotonic here. But so essentially, you're looking for more of a linear solution, so an O of n solution. And this is really important because in a linear solution, like, as trivial as what I'm going to say might sound, you go through each element by one, but you touch only each element once. And that might sound obvious, but it's actually important for getting this problem. If you actually think about it fundamentally, then you'll see what I'm talking about as I explain it more. Anyways, let's look at the trivial test case. And the other test case is, unless you have like an algorithm to already solve the problem, like the test cases are useless. Like you can figure them out. If you figure them out with like an algorithm, then you can like what I'm basically saying. Figuring out the test cases will probably figure out the actual problem, because you like they're not obvious. I guess. I mean, I don't really know, but they don't explain it, so I don't think the test cases are particularly useful here. So, but I do think you always look at the test cases no matter what. And actually, the first test case is actually useful. And you might say, well, what do you mean it's useful? It's just negative two, negative two, negative two. They're all the same. So obviously you increase everything by two. Zero, 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 right? You take this entire array, you apply operation three. You apply that three times. And the reason why I say this is particularly useful is because it shows us that, hey, if we can get all the elements inside the array to be the same number, then we essentially all we need to do is for how many operations it takes us to get the array in for however many operations it takes us to get all the elements to be the same number, we can just add that number, let's say it's x, plus the absolute value of the first element, right? Because or it could be the first element, right, or whatever, because whatever we choose, we just need to keep track of the common value among everything, right? The value that is shared between all elements, which is negative 2. And so what I'm basically saying is that if you can get the array into a state such that every single element is the same, then the question calculating the minimum amount of moves is very trivial from there. So this is where we should assume that let's assume that it's always optimal to get everything in the same number with the same number, right? Because it's convenient, right? Like, you need to note that the most optimal solution in this case is technically just the most convenient solution. It's basically you design an algorithm such that every element is the same, because it leads to the convenience like this where we can just increase every element by 2 and get 0 0 0. So assume that the most optimal algorithm is basically the most convenient algorithm, which makes intuitive sense. Because, like, why would I not try to get all of them the same, right? Like, if I try to get them different, I'm just like pushing myself further and further away from the goal of getting all of them to equal 0. So once you assume that the most optimal algorithm is the most convenient solution, or the most, or they're biconditional, like the most convenient solution is the most optimal solution, and vice versa. Once you assume that, then you can kind of solve this problem, because what I'm going to say is, without loss of generality, right, let's assume that a1, a2, all the way to a sub I, let's assume that these have, for whatever reason, let's just assume that these guys in blue have all the same value. So I'll try to do this, like, maybe. Let's assume that these guys in blue have the same value. So these have all the same value. Maybe the common value, for example, is 1 1 1 1 1 here. We're just going to assume that without loss of generality. And why is this assumption valid? Because we can always assume this, because imagine you have the array 1 2 3 4 5, right? Essentially we're assuming that there exists a prefix such that um, every single element in that prefix has the same value. And obviously the base case of that is just the first prefix that will always have the same value. So even if we don't have any other prefixes that have the same value, we're always guaranteed for the first prefix to have the same value, and all the elements in that prefix will have the same value. We're always guaranteed that. So therefore, we can assume this without loss of generality that this is the case. And let's just assume that it's up to a sub I. Okay. So then we note that these guys, and maybe I should have done those guys in blue, but then we note that a sub I. Let me actually do this in black. Then we know that a sub I plus 1, a sub I plus 2. I do this to a sub I plus 3, and then dot dot dot. A sub I plus 3, all the way to a sub I, or a sub n. We know that all these guys don't necessarily have a different value. I mean, they might. I mean, it might be some edge case, but not necessarily the same value. So not necessarily same value. And here I'm going to make this distinction that this is guaranteed same value. So here we're guaranteed same value. We're going to assume that we're guaranteed same value, right? And why am I doing this? Well, look, this shouldn't be like some sort of contrived assumption, because we already said that, if all of them have the same value, then it's extremely convenient, because at the end we can just add 2 to every element. So let's assume that we have some sort of instance or some sort of algorithm that guarantees that the ith prefix has all the same value. And we're always guaranteed this, right? Because I equals 1 will be guaranteed this for I equals 1. So we can assume this, right? So let's just assume we have our algorithm, which we don't even know right now, already fi- took care of the ith prefix, and they have all the same value. And then these guys have not necessarily the same value. Well, think about it. If I've already so then let's think about the cases here, right? If this has not necessarily the same value, then I obviously want to make a sub I plus 1 have the same value, right? So to get a to for us, so for essentially what I'm trying to say is that for us to maintain our convenience most optimal solution, we must make a sub I plus 1 equal to a sub I, right? Because when we make another element the same value, then we're maintaining our convenience. Our convenience is for all the elements to be the same. That's what I basically mean for our convenience. And if we make a sub I plus 1 equal to a sub I, then we made the solution more convenient, quote unquote convenient, because then we can take the I plus 1 suffix and easily just apply this operation here, or apply a decrease operation. We're just guaranteed a very easy solution like the negative 2 solution, and it would also be like 2 2 2 would also be very convenient. So for us to maintain our convenience, or basically get this optimal algorithm, right, for us to get us closer to the optimal algorithm, it should be obvious that we should make a sub I plus 1 equal to a sub I. So how do we do that? Well, we obviously look at the difference, right? So let delta equal the difference here. Let delta equal a sub I plus 1 minus a sub I, right? We take the difference because we're trying to see that how, like, we want this to be true, right? We know that you could take this with a sub 0 if you wanted. It doesn't really matter. We're just using a sub I because it's next to it, right? Whatever, it doesn't really matter. We just need to make sure that, maybe I even used a sub 0 in my code, I don't know, but we just need to make sure that the value that's shared among this, right, we subtract that from a sub I plus 1, and that's basically the change, the delta that we need to make to a sub I plus 1 to make it the same value. So then we have to observe cases. Let's observe the trivial case, like case 1. Let's observe the trivial case such that delta is equal to 0. If delta is equal to 0, then we move on. We are good. So this is check mark, right? Like, we don't need to touch anything, right? We've already achieved this case. Case 2. We've already achieved this goal, not a case. Case 2, delta, let's delta is greater than 0. If delta is greater than 0, then in this case, we note that we need to basically decrease a sub I plus 1, right? Let's just, like, for example, if this is 10 and this is 5, right? And these are all 5s. Well, obviously, in order to get them the same value, we need to decrease, um we essentially need to decrease a sub I plus 1, decrease it by 5, right? And the way we do that is we can select red suffix, and then decrease every single element by delta. And if you do this, then we can easily achieve this. And obviously, we're not going to go through and decrease every single element by delta. That's inefficient. But there's a very easy thing that we'll do, and we'll look at that in the code, right? But this is essentially just the algorithm that we're designing. Now, I'll just do case 3 here. Case 3, obviously, we have delta is less than 0. So then what we do is select red suffix, right? And decrease every single element by delta. Because now we know that there's no way to, because we know it's a less, right? So if we know that a sub I plus 1 is less than the common value among the blue prefix, then we know that, like, we need to increase it, obviously, but we can't do that without increasing the entire array. So instead, we just decrease the common value in the blue suffix to delta's common value. So we don't affect a sub I plus 1, we affect the prefix that preceded a sub I plus 1. So select no, I shouldn't say red suffix, select the blue prefix, and then decrease every single element by 1, by delta. And this way, if we do this, we can just iterate through every single element and just apply this logic, right? Deal with these cases, and then easy. It's that easy. That's basically the solution. And I'll try it with a test case. But basically, what you need to note is that you, like, the motivation, I guess, for the solution, to finding a solution, is that you see that it's very convenient here, right? And you're assuming that this is going to just be one linear sweep. So essentially, at every element, you're trying to, like, resolve it. You're trying to make sure that you don't have to come back to it again because it's a linear solution. And to do that, we can assume some sort of convenience. We can assume that a sub 1 to a sub I is already good, and then we can use that and then just say, how do we proceed from there? So that's kind of how you get the solution from here. And this will just guarantee this sort of convenience, and it's always just optimal. I mean, I think you could also do this from the back. You could also do it from the back too, like assume that this suffix is good, but it doesn't really matter. They're both like symmetric cases, right? Obviously, like by symmetry they should be the same, so we don't really think about that too much. But this algorithm does guarantee that you always get everything to zero, and it should be pretty intuitive that it makes sense because it's the most convenient, which is not necessarily the most optimal, I will say, but it takes us to like some sort of convenience like this. And I'll go through a test case, right? Let's go through because this is I kind of did this more like abstract, not with actual like numbers. Let's go through 4, -4, or let's go to, yeah, why not? So let's apply the algorithm on 4, -4, 4, -4. So we assume that, right, this is already all the same. Then we look at -4. We're like, okay, we want this to be the same as 4. So we select this prefix, or we select this suffix, and we increase it such that it is the same. So if it is, then we obviously have 4, 0, 4, or we have to increase it by 8. So we have 4, uh, to increase everything by 8, 12, um, and 4, right? Okay, so then we've used 8 there, and then we move on to this guy, right? Has the same value. We want it to, we need to decrease it, and so if we decrease it, then we just select this guy, and we do our decreasing there. And to decrease this guy, we just need to add 8 again, and decrease this guy. We have 4, um, 4, and then decrease this guy. We have uh, negative -4, right? Because we subtract 8, and then essentially, what we need to do is that we know that this needs to be this needs to we know that essentially we can't really increase this, right? Because we have to increase the entire array, so we just decrease this to -4. So we take the whole entire thing, make this all -4, all -4, and that should just be you could do take the entire array and just do -8. So that's another 8 operations, and then everything's -4, -4, -4, and then we just take it should be +8, and then you take the entire thing +4, um, and then yeah, then everything's 0, 0, 0. So then it's 8 times 4 plus 4, which is 36. That's the right one. Right. Yeah, it was 36. I remember, but I don't know why. Okay, so I obviously made like a mistake there because the answer was 36, but like the answer was 36, like, and but like, you understand how the algorithm works. I feel like this is a good explanation, but like not my explanation, but like I feel like this was a good enough explanation that you don't really need another example. I kind of messed that one up somehow. I think I forgot another thing, but you basically see what it's doing, and yeah, you see that was 36. So let's go over the code now. That was an awkward example, but essentially you take in n, then you take in your array, and I honestly should have just used like type def long ll, but I didn't do that. You just C++. But take in your n, take in the array, and we're going to keep track of p and s, and those are the new things that we didn't talk about, and delta. So we take the delta, we just apply our cases, easy. But then we note that if delta is greater, that means I basically, because remember, if delta is greater than 0, then we have to select the red suffix and decrease every single element by delta. And so we have to keep track of the amount of operations that we used, which is s, and then on the suffix, and then for the prefix, if delta is less than 0, then we also have to keep track of the amount of operations we used on that prefix. And then we note that if we've used like s operations, anytime I go on to the next one, I know that it has to be decreased by s. Like for example, if I did like 4, 4, 4, 4, and then let's say I did 5, right? And then 5, 2, 1, right? I know that if I make this 4 by decreasing the entire suffix by 4, I need to make sure that when I get to 2, I don't take the element as 2. Technically, it's 2 minus 1 now. So that takes care of that. And then after that, you could just simply print out the answer, which is the amount of operations on the suffix and plus the prefix, plus the fact that you have to get all of them to the same thing, because this is going to be all like you'll have like something like negative 2, negative 2, negative 2, negative 2, and you just take absolute value of that and add it on. But the code is pretty easy, and I honestly suggest that after you looked at this, you actually code it yourself. But that is the code if you're interested, and this is a seed. So if you copy it, it will be a seed. And yeah, that's it. Thank you for watching.